All right, so hi again, everyone. Now that we finished with the two first fruitful talks, we'll be moving to the third one, titled Headfirst Reinforcement Learning. It will be led by Azzeddine CHENINE, a research engineer and a Google developer expert in machine learning. Again, if you have any question, don't hesitate to mention it in the comment section. Azzeddine is here to answer. You can start your presentation now.
Okay, so hello everyone. With you today, Azzeddine CHENINE. I'm grateful to start with your presentation entitled Headfirst Reinforcement Learning, where we would be going through the basics and the fundamentals when it comes to reinforcement learning solution methods. So yeah, small introduction about myself. I work as a research engineer at a startup called InstaDeep, where we try to apply reinforcement learning into real-world problems at scale. I'm also machine learning GDE for 1 year now, and for the last 3 years, I've been mainly applying deep reinforcement learning at scale to solve hardware problems or hardware design problems when it comes to system on chips or printed circuit board routing. Yeah. So mainly the content of today's presentation would be mainly based on the reinforcement learning and introduction, which is a book by Richard Sutton and Andrew Barto. It's a famous one, and it's one of the must-read when it comes to getting on board into the reinforcement learning journey. And you can access this book, which is available for free by scanning the QR code in front of you. Okay. So the agenda for today is pretty simple. You are free to ask questions along the presentation, and I try to answer them when each one of these points are done, so we can make the presentation alive and rich when it comes to dialogues regarding reinforcement learning. Yeah, so we start with the link between AI and the reinforcement learning in general, and then we move some of the basics, which are the definitions, what is a framework, what is the reward hypothesis, the state and the action value, and finally finishing with the Markov decision process. Afterward, we would move to the reinforcement learning problems. What kind of problems we're gonna solve when it comes to cracking the reinforcement learning problem, the general problem, I would say. Afterward, when we know what are the problems facing us, we will go through the main methods that are used to solve these kind of problems. They are mainly two categories, which are tabular solution methods when it comes to tabular data, and approximation solution method when it comes to data which are not structured, but rather unstructured. We will explain this later, don't worry. Yeah, so first starting with the link between AI and reinforcement learning. I guess everyone here is familiar with this definition by Andrew, Professor Andrew, when it comes to machine learning, which is the science of getting computers to act and make decisions without being explicitly programmed. If you want to highlight this definition, I would give this example here when it comes to predicting the physical activity of a person. So if we want to explicitly program this classifier, I would say, I would do something like this. If the speed of the person is less than 4 kilometers, then the activity is walking. If it's more than 4 kilometers, it's running. Then I would add more if blocks when it comes to cycling or sprinting, for example. But what if the person is golfing? Now the physical activity doesn't fall within our distribution that we explicitly set to the model, I would say. So here it comes the role of machine learning, where we can, instead of providing the rules, we rather provide the data and the labels. And it's for the machine learning model to extract those rules based on a function approximator that we call machine learning models or deep neural networks. So here is an example you're familiar with. You have an image of a person doing a physical activity. You have what we call a convolutional neural network. If you're not familiar with the term, then it's okay. It's just a function approximator. It takes an image and then try to classify this image based on categories of physical activities you already provided. Yeah. So at the end, we classify the physical activity. Then you would have an efficient function approximator after many trials and errors and optimization techniques we use to make this model very efficient. Yeah. So we mainly call this models smart models because they are able to make decisions on their own to achieve a goal. Semantically, the goal is to predict the image, predict what I would say, predict physical activity from an image. But technically, the model is just trying to what we call optimize for a loss that we defined. And we don't find only image classification models, but there is a family of tasks these machine learning models are nowadays optimized for. Mainly, I would highlight some of them. Some of them are what we call supervised learning. It's falling mainly when to classifications tasks or regression tasks. So for classification, you have image classification, object detection, for example, or generative models, or translation when it comes to sequence models. And also we have unsupervised learning when it comes to clustering, for example, identifying populations in non-labeled data, or also association when it comes to recommendation systems and join embedding training, sort of. Yeah, don't worry about this. Mainly these tasks are all, like I explained, trying to optimize for a single point where we want to make the loss very low. But the question we are asking now is that what we will do when it comes to task where we want to optimize for a goal. Let's say a goal where the uh, like the manifestation of the behavior is done via a sequence of actions and not only a single action. I will give you an example. Let's say you are playing chess, or you are having a self-driving car that you want to get from your home to your work office, or you have a robot playing footballs. Those sort of problems try to optimize for a goal that is optimized for after sequence using sequence of decisions. So the end goal for chess game is winning the game, and winning the game involves doing a lot of smart moves that would eventually lead to beating your opponent. So actually, you're not optimizing for a single point, but you are optimizing for sequence, and it's totally different problems. You can sacrifice one of the element of the chessboard, so you can do smart move after. So it's not about optimizing the loss for each point, but rather optimizing for the cumulative outcome of these actions. So let's take the chessboard and try to develop the idea of reinforcement learning when it comes to chessboard. First, what you are trying to do, as we said, is that you're trying to learn an optimal behavior. In reinforcement learning, we call this a policy. And you would learn this by interacting with the world or with an environment, which is the real term, like the technical term when it comes to reinforcement learning. And the challenge here is that you won't be provided by labeled data, I would say, or by examples of how you should behave, but you rather need to learn this behavior via interaction with an environment. Some of you would say, okay, I'm interacting with the environment, but how I should learn is the same thing as babies learn. You learn via feedback. So there is an environment, there is what we call an agent trying to learn a policy. And each time you interact with the environment via an action, the environment would give you feedback called the reward, which is the reward signal. Okay? This reward signal can be given for each action, let's say, or can be also given after the end of a sequence of actions. For example, if we want to play chess, then the reward is either you lost or you won the game. It's not how good your move was, because you don't know how good is your opponent. Maybe your opponent would counterattack your moves. So this is an example. Or it can be that, for the example, like we explained of self-driving car, is that how short, like how close you are to the target. Maybe each time you get closer to the target by 1 meter, I would give you a reward, which is positive. And each time you get far from your target by 1 meter, I give you a reward, which is negative. So it depends. And we call this type of rewards either immediate, like chess, or either sparse reward, like means it's not dense enough for the agent. But also, always there is technique to learn in such environment. And all these actions and the interaction with the environment are done in what we call a finite horizon. Most of them. There are problems which are done like without, like for example, predicting stocks. It's stocks like Denver Ant, so it's not finite. But in this presentation, especially, we will handle problems that are finite and that have a limited horizon that we call an episode. And each episode has multiple time steps where the agent try to optimize its behavior within. Okay, if there is any actions, if there is any questions, please feel free to ask within the chat. Okay, now we finish with the basics. We understood what is reinforcement learning trying to do, what is trying to learn, the reinforcement learning trying to learn. Now let's try to include some definitions that would help us make the sort of the basics, like the baseline of what we want to build on when it comes to solution methods. Okay, first, we went through the interaction of the agent with the environment via actions, having the reward, etc. But we need sort of a formulation of this. So we call this, like these interactions, the reinforcement learning framework, where we have an agent, as it's drawn here. We have an environment. The agent tries to give an action to the environment. The environment then responds with the reward. It can be a reward of 0 if there is nothing to provide, or it can be positive or negative, for example. And also it would give the agent the results of the action on the word, which is the next observation. Let's say you moved something in the chessboard, then what is the outcome of your move? Okay? And usually it's notated like this. There is the observation noted by O of t, which is the observation within time step t, the action A of t, which is the action within time step t, and there is also the reward and the next observation. Okay? And as we said, when the agent interacts with the environment, there is a reward. And some of you would say, why we need a reward? I briefly went through it when I said like babies learn. But theoretically, we have what we call a reward hypothesis, which is the hypothesis that any goal in the real world that involved either sequence of decisions or a single decision can be formalized as the outcome of maximizing a cumulative reward. It can be a single, then the cumulative reward is only one reward, or it can be a sequence of decisions where the reward now is the sum of your rewards that you like took from the environment during your what we call an episode. Okay, this hypothesis is the base of reinforcement learning, which make reinforcement learning actually learn, because without reward, there is no feedback that would allow us to sort of make the agent behavior more, let's say, aligned with what we envisioned for. And as we explained, the reward is the goal is to optimize for the cumulative reward, and the cumulative reward within an episode we call what we call a return. Okay, it's notated G of t, which is the let's say the cumulative reward starting from time step t till the end of the episode. And I want you to remember well this term, which is G of t, is the return. Okay, and we can define also G of t in a sort of recursive manner, where G of t actually is the reward you get immediately after executing your action, plus the return of the next state following a policy. Okay, so if you have a series of action, then if you take this term alone, it's RT plus 1. But if you start from RT plus 2 till the end, then you are basically calculating G of t plus 1. This recursive formula would help us when it comes to creating solutions for such problems. And sometimes in literature, you find that there is sort of what we call a discount factor falling between 0 and 1. And it's mainly used to express how much the agent cares about the reward he's getting immediately versus the reward he's getting later in the episode. So if the gamma is 1, then there is nothing being discounted here. Everything is multiplied by 1. So the agent would care about all the reward he's getting from executing all the actions after time step t. If gamma is less than 1, then having gamma to the power of t, capital T minus t, it means that the number would get smaller and smaller the bigger your episode would get. So you are caring more about the reward you are getting at start of within 2 steps, 5 steps, 10 steps from your time step t, and caring less about the reward occurring at the end of the episode. For this presentation, we don't want to make things complicated. We want to keep the gamma set at 1. So basically, you care about the full, the reward of each action. Okay. So now we said that what we are trying to do is to optimize for the cumulative reward. We want our agent to score the best possible cumulative reward starting from time step t. And in reinforcement learning, we define what we call a value function, that would, like, for example, highlight starting from time step t, which is at state t, and following a policy. The policy can be random policy or optimal policy, it doesn't matter. But following a policy and starting from state st within time step t, what is the estimation of the reward you would get following that policy? So now it's an estimation. It's not an accurate value, but an estimation. And the goal of any reinforcement learning solution is to make this estimation as close as possible to the real value. You won't have real values because there are a lot of factors that would affect that, but you want a good estimator for your value function. And the same as we defined the return, so we define the return as rt plus 1 plus gt plus 1 as I explained, we can define also the value function of state recursively, where the value function of state s is the estimation of rt plus 1, which is the reward you get immediately, plus the value function of the next state. Okay? So we have a value function that would try to estimate the return that you would get following a policy. That policy wouldn't be optimal or wouldn't be also random. It can be any policy, okay? This is one. The second definition we have, the third definition I would have for today for you, is the state action value. We said here that starting from state and following a policy, we have an estimation of the return. Now we want to have something else. We want to say starting from state at time step t and executing an action A at that state, then following a policy, what is the estimation? So now you are adding another factor, which is you are making action A within state S and then following a policy. So it's same thing, just when it comes to rt plus 1, now it wouldn't be sort of estimated because you have the action you are executing on that state. So it's the same definition. It can also be defined recursively, which is rt plus 1 plus the value function of the next state where the action chosen by the policy is being executed. And the action value function is what we call the Q value, is what we call the backbone of the paper called Q learning, okay, or deep Q learning, I would say. Okay, so we learned about the error framework, the value function, the action value function. The last definition is for what we call the mathematical formulation of the error framework, which is the Markup decision process. You'll find this definition in any paper that would try to solve any reinforcement learning algorithm. So if you want to define your framework of reinforcement learning, first you need to define states. What are your states? All your state maybe, or what is the nature of your state? You need to define your actions. and you define what we call the transition function, which is having state and executing that action within that state, how your environment would transit to the next state, and how it would respond by a reward. So let me explain it here again. You have an MDP, which is just a tuple of state, action, transition function, and a discount factor. The state are all the states. Let's take the example of chessboard. Then you can have million of states of chessboard. These are all the states your environment can fall in, okay? Or it can be an image. It's not structured data. It's unstructured, so you would just define the height and the width and the depth of your image. Or let's say you have your actions that are possible to take. So let's say in the case of chess, then move this element of the chessboard to this part of the chessboard. It can be a joint action or it can be a singular action. The transition function is what we call the formulation of how your world, how your environment model is behaving. It can be deterministic, so you have the model of the world. It can be non-deterministic, and now we say that you don't have the model of the world. For the chessboard, you know exactly your transition function. So if you move chessboard element from place to place, you know that it would end up at that place. There is no probability that it would fall from the board, it would move into another place, etc. So this is what you call the transition function. And also you have what we call the discount factor, which is the element we explained before, how much you care about immediate action versus actions happening at the end of your episode. Okay, and the Markov decision process followed the principle that the future is independent from the past given the present. So your current observation or your current state, your current agent state, would resume all the trajectory that the agent happened to take before that time step t. If it's the case, we say that the state is Markovian, and if not the case, then the state is non-Markovian. And it's hard a bit when it comes to non-Markovian state to make them Markovian. Some people try to add horizon data to the state so they can express what happened before, but the quote-unquote rule of thumb is your present, your future is independent from the past knowing the present. If you know the present, then you don't care about what's happening in the past because you already know that from the current observation. So as a recap, we went through some of the definitions quickly. We went through the MDP. We know that every problem can be formalized by a goal, and we went through the what we call the agent components, the state, the value function, the policy, and the transition action, or what we call the world model. Okay, let us try to have an example so we can understand better what it means a value function that we will be using after. So let's say you have a maze. In this maze, you are trying to get from start to the end, and the action you would have is north, east, south, west. And for each move you would take, you would have -1, okay? You are provided with a policy, which is an optimal policy of how to behave at each state, okay? And we want to calculate the state value function. So I'm at this state. At this state, following my optimal policy, I need only to go right, which would lead me to the goal. So if you want to take the reward, the value function definition, we would say it's only RT plus 1, which is -1, okay? If I'm at this state, also I need to move right. So it's RT plus 1 plus the value function of the next state, which is the state before reaching the goal. Then it's -2. And each time, as you see, following this policy, which is optimal, you would find yourself applying the definition of a value function. You are adding -1 each time you go backward through the path, -3 till -6, -14, -15, and -16. Because starting from the start and ending to the goal, following this policy would need 16 moves. It means that you have 16 multiplied by -1, which is -16. If there is any question regarding this, please ask in the. I have question here. An episode is an iteration. I wouldn't call it an iteration because we will use this term after. An episode is a finite horizon where you would apply your actions. So if we take this example here, if I move using the optimal policy, I would take 16 moves to reach my goal. Now the episode is done because I reached my goal. So it's a finite horizon where my actions are applied. Okay, I hope this definition is clear. And we will use this term after, so no worries. Just don't confuse the episode in iteration. It's not an iteration. Okay, let's move. After defining the some RL sort of basics definition, we move to the what we call the error subproblems. So the error is the general problem that you are trying. Reinforcement learning, it's the general concept you're trying to apply, and underneath you're trying to solve some of the basics problem. We count the first two problems: it's learning and planning. Sometimes, as I said, the environment is known to you. Let's take the environment. Let's take the chessboard. You know exactly where each action would lead, and you know exactly if your opponent apply an action, where it would end up, like where the chess element would end up being. So you have your understanding of the model of the world. And once you have the understanding of the model of the world, what you try to do next? Plan your strategy, plan your actions, so you can get the best reward possible at, let's say, winning the chess game. But sometimes the environment is not given to you. You need to explore your environment and you need to understand the physics of your environment. Let's take this Atari game, for example. Once you give this Atari game a child, to a child, it will start to play this game. He doesn't have any clue about how this game would output at the next frame. You can have an enemy coming from this side, from the top, maybe from the bottom. Who knows? I never found out that it comes from the bottom. So what I need to do to make sure that my understanding is right for this environment exactly, I need to explore my environment and accumulate as much as experience that as I can, so I can have a rough understanding of my model. So what I'm doing now is that I'm learning the model. So this is the problem of learning and planning. First, when you are given an environment, you try to learn it. If it's given to you, that's great. You don't have to learn it because it's clear. Sometimes it's not, and you need to learn your environment. And once you learn it, you start planning your actions given the model you learned about the world. Okay. In this presentation, we want to deal with sort of environment where the model is. We need to learn the model. We will just deal with the environment which are given to us. I mean, the model of the world, the model of what we call a model in reinforcement learning. Okay. And basically, we will deal with models with smaller state space so we can make the algorithm trivial for us. The second problem is the prediction and control problem. It's a core problem when it comes to reinforcement learning. So we start with the prediction. As we said, there is a value function where you are trying to have a rough estimate of the cumulative value you would have following a policy. So the policy now is given, and they are trying to predict, following this policy, what is the return that I would get. Now, this is a prediction problem because you are trying to predict a value, a continuous value, given a policy. You are not trying to optimize your actions or change your action distribution, etc. You want to just predict how good is this policy by having a rough estimation of the return. This is the prediction problem, or simply predicting the value function. And there is also another problem called the control. Okay, now we predicted the quality of our policy using a value function, let's say. how I can change my action distribution so I can have better outcomes when I evaluate next time. This is a control problem because you are trying to control your action sequence so you can optimize eventually your return. Okay, so remember this: the prediction I'm trying to optimize. I'm trying to optimize my estimation of the return of the policy using the value function. So I'm basically, quote unquote, I'm trying to have a good value function. And when it comes to the control, I'm trying to take the best actions that would lead to the best outcomes. It can be that you are trying to, let's say, shift the distribution of your actions. But for our case, in this presentation, we would do it in a way that it can be trivial for some, I would say. So let's say you have a value function, okay, of state. Then if you want to move at the next state, as we explained in the maze, what is the best action you would take? I would bet that the best action you would take is the one leading to the state that has the best value function. So now you say what we call you are acting greedy. You can define a policy using a value function, where you take the action that would lead to the next best state when it comes to value function. And we will mainly use this hack to define the policy. There are other methods that try to learn a policy directly, but it's out of the scope of this presentation. Okay, now we learned all the basics for this. We try now to discover what are the solutions, the solution methods available for us to solve both prediction and control problems. First, we start with the tabular solution methods that will deal mainly with tabular data. We will explain it in a bit. So in tabular solution methods, you have model-based, model-free. I will explain this after, but I think you already have experience with that. At model-based, you have the model of the word. Let's say just model-free. You don't have the. Let's say you don't have the model of the word. Although we would deal with the environment where the model of the word is given, but we don't need that. We don't count on the model of the word given to us or not. And we will define each methods and each sub-methods individually and walk through the algorithm for these. Okay, so I will explain briefly what is tabular MDP. It's mainly like sort of an MDP where the state and action space are small enough and can be represented via an array. So let's say the maze here, you have 27 state, 4 actions, a reward of -1 for each step. You can just take an array where each step, each state has a hash, and now you can represent your state space with a table. And the good thing here is that we can like calculate the exact value function and the exact action value because the state space is small. We don't have to estimate because we can give exact estimation, which is the accurate value. Okay, so the first family of methods we will explore is dynamic programming. And this is why I told you remember the recursive formula of defining the state, defining the value function, sorry, or the action values. Okay, so when it comes to dynamic programming, it refers to algorithms that can be used to compute optimal policies given perfect model of the environment. That's one. And it tries to relies heavily on the concept of the MDP. And we start with the first sort of sub-algorithm, I would say. We try to evaluate a policy. So you are trying to have a good value function of your policy. So let's say you have a policy P, okay, or policy pi in English. What we will do is that we will iteratively go over all the states. So for all the states, we try to go over all the states and calculate that estimation. And if you want to calculate the estimation of RT plus 1 plus gamma of the next value, the next value function of the next state, the value function of the next state, sorry, you would just multiply the factor here, which is the R plus gamma VP of S prime. We say that this is given, so the environment is known, we say it's 1, and you just multiply it by the probability of taking that action, as if you are taking an average of the value function of the state you would end up at. So let's say you have a maze up, down, right, left, then you will multiply the value function of, you would multiply the probability of going up by this factor, which is the reward you would get by moving up, plus gamma multiplied by the value function of the state located above the current state. And the same thing apply for the left state, the left cells, the cells under you, and also the cells on the right. So if we look at the algorithm used for this to have our value function, which would be an exact value function actually for that policy specifically, you start first with filling the value function of all the states you have to an arbitrary value, except the terminal states. In the case of the maze that we explained before, it's the goal state because it's terminal. Then you would define what we call the convergence threshold. We called gamma, sorry. We said we loop through each state. So recall always the example of the maze. You would loop through all the states of the maze. And for each state, you take the current value function, okay? You store it somewhere. And then you would calculate the new value function, which is the probability of going each direction multiplied by this. This is 1. This is the reward of you moving, so it's -1, plus gamma multiplied by the value function of the next state you would end up at. And then you would have the value function for that state. Then each time you have a new state and the bed state, the new state and the out state value function, you would take the difference between the two, okay? And if the threshold is less than, if the value is less than the threshold you set, then you reach state of convergence. And now the algorithm is basically done, okay? Now, let's say we have our value function and we wanna improve our policy. We wanna now solve the control problem. It's not relevant to use the value function directly, but we would rather use the Q value. And as we said, we can take a policy by basically just taking the action attached to the best Q value, which is this definition basically. The policy regarding state S, or the action that I would take given state S, is the action that would maximize this quantity, which is the Q value of the state joined by the action, okay? And it's simply the arguments of RT plus 1 plus gamma multiplied by the value function of ST plus 1. ST plus 1 is simply the state that you end up at executing action A. And you already have the value function from the policy evaluation, so you can carry on with the algorithm too easily. If we take a look at this algorithm here, this part, then it's the same thing as before. First, you assume that the policy is stable, so the policy didn't change after you execute this loop. Then you would simply apply the formula that we explained, is that for each state, you would take the action corresponding to the maximum quantity. And then if the action distribution didn't change, then you simply reach state of convergence. And most of the time, you will find that these two algorithms are applied jointly. So first, you endlessly loop through your states till you reach state of convergence when it comes to evaluating the value function and evaluating your policy. Once you're done with that, then you move to the control problem and you try to improve your policy via policy improvement. The joint use of policy evaluation and policy improvement is called policy iteration. And this is why I said that the episode is not it's not an iteration. The iteration has another meaning when it comes to reinforcement learning. And iteration after iteration, you are getting closer to the optimal policy, which is described here. So first you start far from your optimal policy, and with each iteration and acting greedily, you are getting closer and closer, and you are having better estimate of your value function and better action distribution that would correspond to the value function eventually. I say eventually because it's proven that it would converge. We won't go through the math for this presentation, but it's already proven. And mainly it's just the iteration between evaluation and control that would lead to the optimal policy at the end. Okay, now we move to another state of methods called the Monte Carlo methods. So this Monte Carlo methods assume that you don't have any understanding of the world, so you don't have the model, and you would learn directly from experience. By experience, I say it's the state, the reward, the action you applied, and the next state. And it's very famous when it comes to solving reinforcement learning problems. So the first method that we will take is the first list Monte Carlo, and we try to solve the prediction problem using this algorithm specifically. We know that the value function is just trying to have an estimate of the return. So we are trying to estimate g of t, which is the return starting from the time step t and following policy pi. And an acceptable estimate would be just the average that we had after following a policy pi and always starting from time step from state t, st, okay? And the algorithm would simply count the return for time step for state st and then average them. And that would be the value function of state st. So as I explained, you loop forever. So you keep looping, and each time you generate an episode following a policy. And following that policy, you would have the state, action, reward, next state experiences, okay? The return, you initialize it to 0, and you loop backward. You loop backward because you want to sort of do it using dynamic programming, sort of, and you are using the recursive definition of the return, which is the reward I get now plus gamma multiplied by the return, the previous return, which is gt plus 1. And if you encounter the state, you would check if you had already visited within the episode. If not, then you just append that return to table, a giant table of returns you had encountered by after looping and executing many episodes, and you would take the average of that return. Okay, so now we move to the first visit Monte Carlo algorithm when it comes to the control. So giving an arbitrary initial policy pi, now let's say we have a policy pi. We had estimated the value function. Now we try to estimate the action value v pi, okay? And simply instead of averaging the value function of the state S, we try to average the return, which is the Q, the action value of the joint of the pair ST and AT. And it would be simply similar to the one we explained before, except that now we won't look for the state, but you would rather look for the state action. And each time you encounter the pair, you would take the average of the return. And now you would have your estimation of the action value of state ST and action AT. At the end, you would just act greedily and take the action corresponding to the best Q, or what we call the action value. Okay, Now we have a problem with the Monte Carlo methods. The problem with them is that you need to wait until the end of the episode till you need to iterate over your value function or your action value. Sometimes it's not possible because the episode length is too big. And you have also the high variance problem, because it can be that moving from episode to episode, you have a high variance when it comes to your estimation. And the solution for that is using what we call temporal difference learning, or TD learning in short. Let me check my connection. Do you hear me, guys? I think so. Maybe I lost connection. Okay, I think not. Okay, if we wanna explain TD learning briefly, is the most used sort of methods in reinforcement learning, and it's the backbone of deep Q learning and PPO, proximal policy optimization. And the TD learning try to combine the best of the two, best of dynamic programming and the best also of Monte Carlo methods. It is similar to Monte Carlo methods because it learns directly from experiences without having any sort of knowledge about the model of the environment. And it's also like dynamic programming because it's trying to estimate based on another estimate of the value function of or the action value. And when it comes to estimating based on estimate, we call that sort of bootstrapping. Maybe I lost my connection, not sure. Okay. Let's move to the first TD algorithm that we have, which is the TD prediction, okay? And we say that Monte Carlo methods use the episode return GT. So it relies on the episode return GT, and you only get the episode return once you are done with the episode, okay? But when it comes to TD learning, we don't want to wait till the end of the episode, but we want to update your estimation online. So what you want to use is to define an estimate of GT, which is simply RT plus 1 plus gamma of the next, of the value state of the next state, value function of the next state, basically. But this is an estimate. It's not an accurate value like the return, which is calculated at the end of the episode. So from this, it comes the word bootstrapping. And the joint sum of RT plus 1 and the gamma of the value function of ST plus 1, it's called the TD target. So we're trying to match our value function to a target which is called the TD or the TD target, basically. And the way we calculate the next value function, the value function estimation of state ST, we just take the TD loss. What we call the TD loss is the difference between what we estimated as being the return minus our current prediction. So now we have the difference between the two multiplied by step, which is the learning rate, I would say, and we simply add it to the current estimate. And now, iteration after iteration, we'll be getting closer and closer to a better estimate over time. So mainly this is the algorithm for this. So you loop for each episode. You are trying to, while you are generating the time step for that episode, you would, at each time step, not at the end of the episode, but at each time step, you are trying to update your estimation. So for each step of episode, or of an episode, you would take an action given by the policy you would have. You take the action, you would have the reward at the next state. Then you simply apply the TD update to get the value, the next value function of the state. Okay, and then you continue playing your episode and updating your value function estimation over time. Okay, so we want to compare for a bit Monte Carlo and TD prediction before we move to the control, and explain why we say that Monte Carlo has what we call high variance compared to TD learning. let's say you are moving from your office to from the office to your home, and at each, let's say, time point, you try to change your estimation of the time needed for you to reach the office. Sorry, you reach your home. So once you left the office, you say that it would take me 30 minutes. Then after reaching your car, you would say, no, it would take me 40 minutes. Then let's say you would have highway traffic. You would change your estimation and say it's 35 minutes, etc. At the end, when you reach home, you find that the accurate prediction would be reaching home at 43 minutes. When it comes to Monte Carlo, it would try to optimize for all the points to match your final outcome, which is so all the points that precede ending your series of prediction tries to optimize for that return, I would say. But when it comes to the TD learning, you are just caring about the estimation you would get next. So if you estimated first that you would take 30 minutes and next you estimated that you would take 40 minutes, then your goal is just to match your next prediction. So you're just trying to approximate to the next estimation you had. And this is bootstrapping. The problem here, as you see, once you start changing your value to match your final outcome, you would have high variance. In the other way, the TD learning, you would have low variance, but you can fall into the problem of bias because now you are just looking towards the prediction you have next. So this is just briefly explaining the problem that we mentioned, which is the variance problem when it comes to Monte Carlo methods. Okay, we learned how to do TD learning when it comes to the prediction. Now, how to do the TD learning when it comes to the control problem, and it's basically the SARSA method. SARSA stands for state, action, reward, next state, and action, and they are basically trying to learn using the, as we explained, the action value or the Q value of state and action. And this algorithm is the backbone of the Q-learning algorithm that we'll explain after. So basically what you will do is that you will do what we were doing before. So you choose an action A, you initialize your initial state, you are looping through the episode, and for each time step, you are taking an action. That action can be epsilon greedy. So by epsilon greedy, I mean you flip a coin and either you take an optimal action using your policy or you choose an action at random. And for each step, you would take the observe the reward and the next state. You would also take the next action, a prime. And once you have all the SARSA elements, which are the state, the action, the reward, the next state, and action, you would calculate the TD loss, which is the reward plus gamma of the action value of state next state and the action you would take at the next state minus the action value of the current state and the action you would take. You have the TD loss and increment. You would update your current estimation of the action value of state action, and you would carry on doing this iteration, episode after episode, till you would eventually reach state of convergence. Okay. And the problem here is that you would sometimes have a problem, as we said here, you need to use epsilon greedy because you would have a problem of exploration and exploitation. And this famous problem in reinforcement learning because you find yourself exploring, exploiting what you have, which is the policy you are learning, but at the end you are not exploring your environment, you are not exploring the outcomes of bad actions. So it's sort of a dilemma that we have in reinforcement learning, and the way we solve it is you would use two policies, what we call a target policy and a behavior policy. The target policy is the policy you're trying to optimize for, and the behavior policy is sort of a random policy. Most of the time, it's a random policy or a policy that you learned in the past. So it's not as good, I would say, as the current one you are having. And basically, it's used in Q-learning, where you are trying to take actions greedily, epsilon greedily. So you take actions after flipping a coin, either it's random or following your policy. But at the end, you would get the TD loss by using the maximum Q value of the next state. So even if you are taking actions in epsilon greedy way, when it comes to getting your TD loss, you would act greedily. So now what we call this is the behavioral policy. So now this policy is not certainly optimal because it's epsilon greedy, but this is your target policy. You would like it's common sense that you would take the actions corresponding to the best action value. And this is basically a different tweak of SARSA, which is max SARSA or too short Q learning. So in tabular methods, we explored model 3, which are the Monte Carlo and TD learning. And we explained also the model based, which are the dynamic programming and policy evaluation, policy improvement, and too short policy value, policy iteration. Now we move to the approximate solutions methods, okay? By the approximate solution methods, I give you example here. You are trying to learn how to solve a Rubik's Cube using a robot hand. You can imagine the state space you would have by observing your hand and observing the Rubik's Cube. It's basically endless, and it's hard to present it within a reasonable tabular representation. So what we use for this, we use our famous function approximator, which are neural networks that would try to predict the state value and predict also the action distribution that you would take given an image or given any unstructured data or even tabular data feed it to a neural network or function, a linear function, too short. And in this presentation, we will try to explain. Okay, so we're trying to explain the gradient-based methods that are methods based on backpropagation and getting your gradient to update your estimation of the value function and also for the policy. We go briefly through the definition of derivative, which is simply it measures the sensitivity of changing the value bit bigger or bits lower than an argument x. So if we take this example here, if I move x a bit forward, then I would have a big sensitivity sort of, because my gradient is too high, and it's basically representing how far I am from the local minimum of my function. So the goal here of this gradient-based method is to update the weights of your approximator to the point where you would reach the minimum of a loss or a loss that you predefined, and we will learn how we predefine it. So here, if you want to try the optimize for the value function, you're basically trying to match your estimate of the return to the return itself. So you can simply use what we call mean squared error loss between your actual return from playing the episode and from your estimation of the return. The thing here is that your return can be the actual return based on the Monte Carlo return, or it can be also the TT target. So you are bootstrapping actually. Okay, and with time, you would eventually reach the local minimum of your, let's say, 3D loss if you have 3 parameters within your neural network. Also, there is a trick to apply this type of methods directly to the policy functions, policy action distribution, but it's out of scope of this presentation. I added the QR code here as a homework, so you can go directly to the paper discussing this type of solutions. So as a recap, we discussed tabular methods, approximation methods, and for approximation methods, we discussed basically model 3 methods, which are value approximation. Policy gradient is a homework. I would happy if you can take a look at it. It's very very commonly used, and it's one of the core methods of solving the error problems. The references used in this presentation are mainly as I explained, the reinforcement learning and introduction book we have here in the QR code 4, and also the DeepMind deep reinforcement learning lectures for the year 2021. It's really beneficial, and it's also based on the book I shared with you at the start of the presentation. Yeah, so I'm happy to take your questions if there are any. I see some questions. If there are some questions, please go forward and ask your question in the chat. I know that it's a bit technical, but you can always, guys, go back and go through the slides with the pen and the papers and go through the basics just by applying some dynamic programming or like trivial mathematic stuff, and it will be very, very beneficial at the end once you get the basics, which are, I agree, it's a bit technical for this presentation, but it's a must if you want to get introduced directly to reinforcement learning. Yeah, of course, the presentation I will share it with the team, and they will be sharing it eventually. Okay, see you guys, and have a good night.